Who are you?
Oh boy, I'm happy to be.
I know when I walked in, he was naked on the floor.
Morning, everybody. Morning. Tendency. And then this is a homework for anybody who doesn't have it, so just take one and pass around. Okay. For tonight. To do for Thursday.
What to do? So sorry, I didn't do that. I didn't take it back. That was good. I didn't really take it back.
And then I have your other ones. Again.
Oh, I had a little homework.
I think that's yours.
Struggling.
Jeff. I never had a ask that home before.
I want to.
RD. Jack Swanson. Yay. Allie. Alex. Cody. That's you, right?
I tried something like that.
Is that you, Cody?
Yes.
Okay.
Check plus. I tried one of those ones.
So the plus minus doesn't really mean anything, it just means that you tried harder than the harder.
Oh.
I tried.
What? That hurts my feelings.
Well, I thought, okay, so I put in there that I wanted you to explain why you said your sentence, and if you were just like, I feel like my voice is dark, I didn't feel like that was enough explaining. Yeah.
Put your name on the
That's basically it. Alright, Jenny.
So much reaching.
Oh, no. Michael Hewitt. You do this, don't you?
Yep.
I don't know, ask me. Don't ask me. I always say, I would have to check my work out, check my
Ian's gone and Allie.
What is that? Is that pudding?
Awesome! Do you have your homework for me?
I do.
Cool, okay, so then I have your papers done too. Do you guys want those back or you want me to give them to you later?
Later.
Later, great. So I'll give them to you closer to like a month away from when the papers due. Okay. And then you won't lose them. Okay. Cool, okay, so let's review from last class. Was the homework alright for everybody?
Yes.
So, not bad. Alright. So, who can tell me what the 4 properties of sound are? This is like the stuff that's going to be on the test. One at a time.
Amplitude, spectral, envelope, and duration.
Okay, good. So what's frequency?
It's
It's not pitch. Remember, we had that whole discussion.
It's the not pitch.
Yeah, it's not pitch.
Good one.
Cool. Okay, so what's frequency? What do you measure it with?
Hertz.
Okay, and what does hertz mean?
Cycles per second.
Great, awesome. Periods per second.
Okay.
Right? So periods of the wave. And what's the period of this wave? How many periods does this have?
2.
2 and a quarter. Yeah, 2.
2. Good. Alright, so we got that, right?
Oh, yeah.
Good, and then amplitude is what?
Loudness.
Loudness, good. And how do you measure that?
Decibel.
Good, and what is twice as loud in decibels?
3 more decibels.
Right, exactly. And so if you were going to go twice as soft, what would it be?
Minus 3.
Yeah, and 6 sometimes. Okay, good. And then spectral envelope is what?
Color.
Good, and so how do we get timbre and color?
Different formats. Different formats.
No, not formants.
Oh, different.
We have not talked about
Vowel
formants
shape?
yet.
Different viewers.
The shape of your articulators.
Okay, so what do you do to a sine wave that makes it have timbre? Because sine waves have no color.
Vibrato.
You add other frequencies, right? Which are
Vibrato.
Overtones.
harmonics.
Harmonics.
Harmonics, right? Okay, so if we
Well, we're
took,
doing really well.
no, you actually are doing pretty well, okay? So spectral envelope is when you add harmonics, timbre to a sound, okay?
Okay.
Basically what it is so if I took this, I am an awesome artist, just like Dr. King, okay? So this is a sine wave, the top one's a sine wave, right? So if we added other harmonics to it, it would look like this.
Oh, dear.
Okay? Right, totally. Well, no, any sound looks something like that, okay? Like, because we don't produce sound, sine waves, right? Good. All right. Then what's the difference between pitch and frequency?
Pitch is relative.
Subjective.
Pitch is the perceived.
Frequency is objective.
Right, pitch is subjective, frequency is objective, right? So frequency we measure with hertz, right? Pitch is like an A with whatever tuning or whatever we want, okay? Got that?
Yep.
Good. What's periodic sound?
Anything that,
It's like, has like consistent.
it's what creates a
vibration.
pitch.
Well, which is, okay, so you can have aperiodic sounds, and what else can you have besides, or periodic, I just said the answer.
Yeah.
Aperiodic, right? So periodic has what?
Pitch.
Recurring periods.
Is not.
Periods, right? Which makes it have what?
Duration.
Pitch, pitch or frequency, which one?
Pitch.
Frequency.
Frequency.
Yeah. Pitch is something is subjective, remember? So we can't measure pitch, technically. We measure the frequency of something, okay? Good. Good, and then an aperiodic sound is what?
Not recurring.
Right, and so it sounds like noise, or something like that, okay? Good, what's the wavelength equation?
Wavelength. Speed of sound.
Yep, good, Tommy got it.
So it's 343 over whatever the frequency.
Yeah. And so that, like, the 343 thing changes with what? What makes the speed of sound change?
It's
Temperature.
environment.
Temperature, right?
That's at 20 degrees Celsius.
That's at 20 degrees Celsius. Good, which is like 70 degrees, I think. Or 68, so not bad. That's room temperature. But so if it's like 80, it's a lot closer to like 350. That's why I use 350 for a lot of my equations, just because it changes that much. Okay. Good. Awesome. Decibels, spectral envelope. Okay, what is the harmonic series? So good job, Alex. So if we have a string, right?
Uh-oh.
It's a string, and we divide it into what do we get?
Two strings.
What pitch do we get? Or frequency?
An octave higher.
An octave higher, right? Good. If we divide it in thirds, what do we get?
Higher than that one,
Yep. Good.
than last one.
And then if we do it in quarters, it's what?
The third octave.
Third. High.
Yep, third octave. So it's an octave, a fifth, and then a fourth above that, right? And then what are the next four after that?
A third, a major third.
No.
Minor seven.
Oh yeah, major third. sorry.
Major third, then a minor third, and a whole
minor
seven and a
third.
half step.
It's like it's in
No,
between
major.
minor third and half step, or a whole set.
It's approximately do, do, so, do, mi, so, la, te.
It's more like do, so, do, mi, so, and the seventh.
Oh, there's no la.
Right.
Just immediately.
It's in between la and te.
Got it.
Okay, and that one's like way out of tune. Has everybody got that? So it's basically an octave, then a fifth, and then another octave, so you get the 3 octaves, and then it's a dominant seventh chord above that. That's how we get the dominant seventh chord, in case you all want to know. Okay? Is that clear? It doesn't look very clear.
Yeah, that was definitely not clear what just happened in this.
It's on page 22.
But I also can learn it in my notes.
I also can learn it in my notes. I'm just gonna show you on the PowerPoint. It's this thing, right? Do, do, fifth, do. Dominant seventh chord. This one's way out of tune. Okay? Make sense?
Are you gonna ask a question about your string explanation on a test?
No.
Okay,
You have-
because
you
I
have-
definitely don't understand that interpretation.
You get it from splitting up the string into sections. So it's like that's the easiest one to understand because you do it with your voice. Like all harmonics are present in everything and they always vibrate like that. Okay? They're always like an octave and then a fifth. That they are always like that. Unless they're like differences. We'll talk about when it's different. Okay? Make sense?
Yeah.
Sweet. And then duration, obviously, how do you measure duration?
Seconds.
Or milliseconds, years,
Oh.
centuries. Great. Okay, good. Everybody got that? So that's basically the stuff you need to know from that chapter. Okay?
Beautiful.
And how it works. So you need to be able to apply it like you did for your homework. Okay? Good. Now we get to talk about resonance. Did everybody read the chapter this time?
Yes.
Yes.
Sometimes sound gets
Okay, so there's three parts to making a sound, right? We get the power source, which is like the air, the bow, the mallet, or, so like in the voice it's our breath, right? But you all were very good with your papers. I really enjoyed reading it. You all had like a really good grasp on what you talked about. Even the people who said that they hadn't taken this class before, you had a good grasp, but there's a lot of specificity that we'll get to, okay? Good. Good. So power source, right? Then we get the vibrator. Whatever makes the sound. It has some kind of friction. There are harmonics created there, right? So it's string, vocal folds, lips, drum head, whatever. And then we get the resonator that's afterwards, right? So the violin, body, trumpet, like in the voice's case, it's the inside of a mouth, right? Good. So we have to know what those are. The garboche. Okay. So it's a really unique instrument. It's super, super complex, and it's one of the most complex things that our bodies can actually do. Because the number of nerves that are involved in it and all the muscles that we have to coordinate, it's very, very complex. So like facial expression is like the other one that's close to that, but it's really, really far away. So if you think about how many different facial expressions you can make, and then think about how you can do like 10 times that many with your voice, it's kind of crazy. Good. It's the only musical instrument that incorporates language, so we have to learn our French and our German or Italian or English. Good. The voice articulates with its resonator as well as with the vibrator, and that's a very unique thing to the instrument. That would be like if you were playing a violin and the body of the violin changed size all the time. Okay? So just think about like how weird that is. Okay? So most instruments articulate with the vibrator, like in the case of a trumpet. They change the length of the trumpet so that they can change which overtones they're playing, but they can't really change the shape of the resonator, so it always sounds the same. Whereas we can, so we can go E or whatever, right? And it all sounds like E because we'll talk about that in the next chapter. Make sense? So we can change the resonator. Very annoying. Alright, so this is the definition of resonance. And McCoy wrote it in his book, it's a good place to start. Resonance is the intensification and enriching of a musical tone by supplementary vibration. Good. So there's two important parts of that definition. Intensification and enrichment. The sound is transformed by the resonance. So when we get the vibrator, it has like a very basic sound, and then the resonator will change how that sound is, okay? It also intensifies it, so it actually amplifies it in some ways, which we'll talk about today, okay? That's basically what we're talking about today, is how the resonator can amplify our overtones. The other thing is that with the supplementary vibration, the resonance produces a new kind of vibration that, in addition to the vibrator, so we get colors in our sound, right? So we get the different harmonics that are created. Yeah? Sweet. It's really similar to somebody getting pushed on a swing, like a little kid. So you just make a little motion to push them, and it has a very large ramification where the child like flies away. And if you push them hard enough, they'll fall off. Scientific. It's physics. Alright, there's 3 types of resonance. This was in the McCoy book. There's forced resonance, conductive, supplementary resonance, and free resonance. Okay? Am I going too fast? Okay. Forced resonance. The vibrator is directly connected to the resonator. Okay? So it's like a plucked string on a violin or a piano, and the resonance is the vibration of that string or whatever. Okay? It's physically transferred to the resonator. So it's not in the air. Nothing changes in the room. It's like if I hit the table and the table vibrates, that's the resonator. Okay? That's forced resonance. It's me making it happen. Good. Supplementary resonance. It's a result of forced resonance. So these are the 2 things that are similar, right? They come hand in hand. The surface area of the vibrator, the violin string, or whatever, is small compared to the mass of the air that you're moving, right? So if I'm wanting to make sound like hitting the table, and I go like this, you can't hear it, right? But if I do that, the surface area is bigger, so there's more vibration in the room, right? Good. It's similar to making waves in water. If you have feet versus your flippers, so you can make small waves with your feet, but if you have flippers, you can make a lot bigger ones. Make sense? Cool. So the vibrations we feel are forced resonance. So if we physically create a vibration like this, that's what the forced resonance is. But if we feel it, so like if I have my hand here and I feel the table move, that's the supplementary resonance. Okay? Yes?
So if forced resonance results in supplementary resonance, what's the difference between the 2?
Because forced resonance is the connection between the vibrator and the resonator. And the supplementary resonance is what we feel. It's the motion of it.
Okay.
It really makes sense when we talk about the third one, okay? So the free resonance, compared to free resonance, it's a big difference. Free resonators change the sound itself, and we hear the changes to free resonance, right? So if I change the shape of a trumpet, or if I slide on a trombone, that changes the pitch, but it also changes the way that the instrument is resonating, right? For instance, with my voice, if I go, I'm changing the free resonance because it's after the vibrator, and the shape of the resonating tube or whatever is after it changes what the sound is, okay? Yeah?
So in singing, what is the supplementary resonance?
It's like the vibrations we feel in our head.
And
Or-
what
Or if you feel your chest, and you sing in chest voice, and you go, and you feel your chest vibrate, that's supplementary resonance.
in the chapter, didn't it say that was forced resonance?
It is forced resonance, but it's part of supplementary resonance.
So they're basically the same thing.
They're basically the same thing, but they have the supplementary resonance is what is made to vibrate because of the connection with the vibrator, okay? So like the resonance that happens in the table when I hit it is the supplementary resonance, but the sound in the room is the free resonance,
Gotcha.
okay? Because we also get the resonance of the room. Like if I hit this table in Studi, it's gonna sound different than it does in this room, right? And that's the free resonance. So that's how we get the 3 different parts, okay?
Gotcha.
So the supplementary of it, resonance is actually not what we're hearing really. We're hearing the forced resonance through the air.
Yes,
free
we're hearing the
resonance.
free resonance.
Sorry. The forced resonance is only the vibration of the sound source itself.
That's a supplementary resonance.
The forced resonance is like what you.
Is the vibration,
Just
because I make it happen.
the
It's like we're,
concept of the vibration, not anything that we interact with.
well, it's our vocal folds.
Right, so only at the source itself.
Yeah, yeah.
Got it. And then the stuff we don't hear that is vibrating because of the forced resonance is the supplementary. And then what we do hear depends on the shape of the resonator. is the
Right.
resonance.
Okay,
Got
yeah,
it.
good. So let me explain that again, because it's a good way of explaining it. So we get the forced resonance is the actual, like, vibrating of whatever vibrates. The actual string that's vibrating has its own resonance. The supplementary resonance is what it's attached to physically. So that vibrates too, okay? Because we're not, when we play a violin, we're not playing the body of the violin, we're playing the string. So the body vibrates and has its own resonance frequency. That's the supplementary resonance. Okay? The forced resonance is what it does to the air. Okay? Which is, it's more of a wind instrument thing. So if we get in our voices, we change our shape, or like in the flute, like if we change like how you finger it or whatever, we get different sounds, right? Does that make sense? Cool. Well, I hope you get it right. Okay, good. There's 6 chambers of free resonance in the voice. Laryngopharynx, right? Glottis, the epiglottis, oropharynx, oral cavity, nasopharynx, nasal cavities, and the piriform sinus, right? A lot of you have written something about this down. And I just want to make sure you know that nasopharynx is only chamber of free resonance when your soft palate's down, right? So it's not always a chamber of resonance, and actually when I was writing on your thing, I didn't realize that this is how they taught it, so I like wrote no on some of them, so forgive me. Just so it's only a chamber of resonance when you're using it to actually use the air through it, okay? Cool? Oh wait until you guys are done writing them down. I think I have a picture of them. Yeah, I do.
Wait, did you say the nasopharynx or the nasal cavities from the soft palate?
When it's past your soft palate.
Nasopharynx.
So in your nasopharynx. So the nasal cavities is like in your nose.
Oh, is nasopharynx like
Yeah, it's like
all
this
this
stuff.
cheek stuff?
Mm-hmm. And it's huge. It's a very big space inside there. Really. We good?
30 more seconds?
I'll give you 15.
Is the piriform sinus the same thing as the laryngeal ventricle?
Yeah. And that's where the singer's format comes from. They're like really sure about that now. Whereas like 10 years ago they didn't know. So if you would take this class with Dr. King, he doesn't know that. Onward and upward. Everybody got it?
Yep.
Alright, Miss Helen. Okay, here's a picture of him, right? Oh, it's hard to see. Let me turn down the lights. That better?
Yeah.
That's what we usually do. Right, okay, so
You know.
this section, sagittal, leads from the side, like you're looking at me like this, right? And the posterior view is from behind me, right? So this is the tongue, that's the jawbone, yeah?
Yep.
Cool. Alright, so if we get the nasopharynx, it's right here. Whoa, look at how big it is. Yeah. Oral pharynx, the oral pharynx is basically your mouth, inside your mouth, okay? And hypopharynx is down here, okay? Inside the larynx, so this is your epiglottis, right? That's what closes when you swallow, and this is your tongue, and that's your uvula, right?
Oh, yeah.
You can see. So the piriform sinus is down here. It's on the outsides of where your epiglottis comes out. Makes sense? So it's under the false vocal folds, and it's like this tiny little thing. And they actually have like, so when the trumpet players play, you know how their mouthpiece has like this little cone shape to it before it gets really skinny? The space in between the lips and that mouth shape is about the same size as this. And so they get the same kind of, that's why they're so loud when they play, and we can hear them. Okay?
What is the hypopharynx again?
Hypopharynx? Right here.
Is that like?
So it's like the larynx is right here, cricoid cartilage, epiglottis. It's mostly, it's like where you swallow food through. So you don't ever like sing through that unless you're burping or something like that, right? Cool? Awesome. Alright, so this is the big meat of what we're talking about today is half-length and quarter-length resonators, okay? So a half-length resonator has both sides of it, they're tubes, okay? We have a tube. Our voice is a tube, like trumpet's a tube, something like that. Half-length resonators have both ends are open, okay? See right here? Quarter length have one side's closed.
Got
Big,
it.
big difference. Okay, it does all kinds of. So if you notice, when we have so these are sine waves going through the tube, right? So here we get a whole half a period of one, right? And we get a whole half a period of the other one. This one we only get half of that half a period, right?
Yeah.
Okay. It changes what harmonics get sounded, right?
When one end of it is open.
When one end of it is open instead of two.
That's very strange.
It is kind of weird. We're gonna watch a video about it actually.
Are we closing the one end of the quarter length resonators for study's sake, or is that something that happens whenever it is a certain length?
So our voice is a quarter length resonator.
Got it.
Okay.
So that's for
A
our
flute
purposes.
is a half length resonator.
Okay.
Okay.
What?
Yeah, we're about to watch a video about it. Okay.
All right. Well, let's just watch the video.
Let's watch the video. He's better at explaining it than I am. Okay, so I want to point something out. What he's doing. He's playing. This is a flute, but he's playing it with a clarinet mouthpiece, and this is a clarinet, and he's playing it with a flute mouthpiece. So pay attention, because the mouthpiece is what's either open or closed, right?
Fascinating.
Right.
Okay. Let's start over.
What are these strange instruments? We could call them superpositions of a flute and a clarinet. Here we use them to demonstrate standing waves in sound. The flute is open at both ends, so the air is free to move in and out, but the pressure is close to atmospheric. The clarinet is open at the bell, but at the mouthpiece, it's almost completely sealed by the reed.
She's like our
So the
voice.
pressure is large, but there's little air motion. Let's picture the reflection of a pressure pulse. At a closed end, the air can't move, so the compression pulse can only move back along the pipe. The pressure wave is reflected with a phase change of 0. At an open end, things are different. Here the pressure is approximately fixed at atmospheric, so the sound pressure is near 0. So the pressure wave is reflected with a phase change of pi. The flute has 2 open ends and is roughly cylindrical. So we expect the lowest note to have a period of twice the length divided by the speed of sound, and the reciprocal of that gives the frequency. The clarinet has 1 open and 1 closed end. This time the cycle repeats after the pulse travels 4 lengths of the instrument. So the period of the lowest note would be about twice as long, and the frequency about half that of the flute.
Okay, does that make sense? No. Okay, great. So okay, so the phase of the wave changes when it reaches the end of a tube. Okay.
Can you use another word for phase? Like what word, is that something new or is that a word that, sorry, this is a dumb
This is
question.
new.
Never mind.
Okay. So the phase, if we go, sorry. So if we have tube, right? Like this. And the wave is going down. So this was in the, like this. Okay, let's just say it does this, okay? When it reaches the end over here, and there's a pressure difference, so like in the tube it's got the same, and that's going into an open space, okay? It reflects because it changes going from low pressure, or high pressure to lower pressure, okay? That makes sense? So that sound goes out here, sound, right? But it also goes backwards, because it reflects, so some of the energy goes back, okay?
Okay.
That's what's called a phase change.
So it has
It's
to
the
do with
reflection.
how long the tube is?
No, it has to do with the fact that it's going from in a tube to an open space. Okay? Because it changed, okay? Like if you think it's part of the reason that like stuff sounds different, like if you are talking underwater and you try to listen to somebody, or if you're underwater and you listen to people outside, it sounds weird because it's going through a different medium and it starts to travel. Parts of it get reflected and done. Okay? Make sense? Anybody else have questions so far?
Well, I understand the phase part now.
Okay.
Now, can you explain everything else that happened?
Good. Okay, so so part of it reflects, right?
Yes.
So this right now it's in what part of the wave? Is this compression or rarefaction?
Both.
Like when
No,
it's
no, no.
going backwards?
Compression.
Going right here. Is this in compression? So if it's
That's
above,
compression.
it's compression, right? So when it reflects, it turns into rarefaction. So it starts back down here. Let me draw that with a different color.
Purple.
Okay?
Okay.
So that's what a phase change is. It flips the wave, compression or rarefaction, okay? Because it's a reflection of the wave going backwards, okay? You can also see this like in water, if you watch waves like go from in a like stream and go out into the ocean, like how that affects different things.
And what does it mean when it's 1/4 and 1/2? I didn't understand
Okay,
that part.
so, let me tell. This is complicated, okay? It's okay if you don't understand it, because it's a little like awkward. Okay, so this is. So if we have a half length, right? When we start the sound here, whoops. And we do this, and then it's gonna reflect here, right?
Right.
And because it's open on this end, open, it's gonna have a phase change, right?
Right.
Yes.
The heart.
So it'll be here.
Yeah.
Okay, and then I'll have another phase change here, okay?
Uh-huh.
So it takes half of the length for a sound wave to vibrate,
Half of
We
the
have-
length of what?
of the sound wave.
Can you say that one more time?
It takes half of the length of the sound wave in order for it to have resonance, okay? Let me show you the other,
Resonance in the space, resonance
in the resonator.
inside of the resonance.
So what we're talking about is the sound going from the front of my mouth to the back of the mouth and go boom, 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 and then when it hits the right frequency, it like resonates with itself and it makes louder overtones. Okay? Make sense? So, okay, so if we look at this slide, this is better. So because it's open at both ends, we can start here and then we get the change in phase here, right? So we're going from red to the blue. And so we only need, because this is only the compression part of the sound wave, we only need half of the wave's length, right? So we would have the rarefaction over here in order for it to reflect and be the same on both sides, okay?
Yes.
Does that make sense?
Yeah.
Okay. Because it's closed on this one end here, there's no phase shift when we get to this side. Because it doesn't reflect off of itself, it reflects the whole sound wave, okay? So it doesn't phase shift.
When it hits a closed end, it returns the exact same form as when it arrived.
Right,
But when it hits an open end, it flips upside down and the
Yeah.
compression becomes rarefaction and vice versa.
Yep.
Okay.
and the math for that is like really hard, so you just
Don't
kinda
make
have to
us do
like trust me about
Oh.
it, okay?
Wait,
That's
so, what? Why? Can you explain like the graph that we're looking at? Because I don't see anything. Well, I guess you wouldn't see it if it were reflected the same, because it would just be the same sine wave on top of the sine wave that was already there. But so what is the difference between the red and the blue?
One's the reflection.
Oh.
So if we start with the red here, right, because we always start in compression, because we have to
Right.
compress to make the sound,
Right.
right? So actually, so if you're doing math, you always start with the cosine, right? And you do this, and so it gets down to here, and then, so it's open here,
Uh-huh.
and so it has to reflect, and so it flips.
Can I just need to remember,
Mhm.
compression is that everything above the line or is it just going down?
It's everything above the line. Okay, so if we were looking under the line, this is like the rarefaction of the wave, right? So you gotta remember, rarefaction is not like negative power, it's just it's not compression, right?
Mhm.
Yeah.
And is one of these more conducive to resonance than the other? Like
No.
closed versus open? Okay.
Mm-mm. We'll see what they do. Okay, so now that I've do you all understand kind of what phase shifting is?
Yeah.
Kind of, yes.
Okay, so in the video, he shows it better. Let's watch the video again, and it might be more clear, okay?
Okay.
I do like that guy.
They've got like a whole series of these things you can watch. Okay, so let's watch. If you watch in his graphics, you can see it change.
Why does it not reflect from the
So the air is free to move in and out, but the pressure is close to atmospheric. Clarinet is open bell, but at the mouthpiece, it's almost completely sealed by the ridge.
Right, so it's
The
closed.
pressure is large, but there's little air motion. Let's picture the reflection of a pressure pulse.
Okay, this is what's important.
At a closed end, the
It
air
doesn't
can't
change,
move, so
see?
the
It
compression
stays
pulse can only
dense.
move back along the pipe. The pressure wave is reflected with a phase change of 0.
So it's not changing
Open end,
phase.
things are different.
Changes, see
Here the
it's
pressure is
hollow.
approximately fixed at
Changes.
atmospheric, so the sound pressure is near 0.
changes.
So the pressure wave is reflected with a phase change
Got that?
of pi.
Yes.
Cool, let's keep watching.
The flute has 2 open ends and
Changes,
is roughly cylindrical.
changes.
The two-dimensional graph really
So we expect the lowest note to have a period of twice the length divided by the speed of sound, and the reciprocal of that gives the frequency. The clarinet has 1 open and 1 closed end. This time the cycle repeats after the pulse travels 4 lengths of the instrument.
Okay, so that's really important. It takes 4 lengths for it to get back to where it started when it got there. Because it has to go, so it starts here, it's in compression, right? Okay, compression, and it switched to rarefaction. Rarefaction, so this is 2, right? So we've gone 1 length, then we switch it, right? 2 lengths, so that's half, right? So, but we're still at rarefaction because it's closed,
That's right.
okay?
And that's why,
Wait,
like,
so why is it 4? Then you come back.
Wait, so if you say it's 2 lengths, how is that half?
Let me show you what this.
well, and because it's closed, that makes sense because the clarinet, even though it's like the same length relatively, has lower pitches, right?
Right.
Gotcha.
Yep. Okay, so we get these graphs work really well. Okay, so this one is half length, right? Okay, so if you notice, see how it's dense now and not dense? So the dense is the compression, that's the rarefaction, okay? Now remember, this happens at the speed of sound, so it's like super, super fast, okay? And I've seen like where they try to model it really slowly and like you can watch it build, but it's really hard to understand when you watch it finish. Okay, so it changes when it gets to this end, right? So it's gonna change to open, but now it changes back. So the sound, if it starts here, it only has to go twice across it to get back to compression, right? Compression,
And that's why
Flips.
we call it a half length.
compression, because it goes twice, it goes down and back, and then it's back to the same as it was when it started.
So it doesn't really make sense why that's called half length instead of 2 length. But that's just is what it is.
Because it's half the length of the sound wave.
Yes.
Because we're only talking about the compression, we're not talking about compression and rarefaction, right?
Let's just
But you-
go on and see
yeah.
if it even matters.
You can have so many different lengths of sound waves.
So this one takes 4, when we get to the open, it takes 4 to go down, right? So if we go back down here, we're gonna start with compression when it gets back to that, okay? Compression, 1, 2, 3, 4, and now we're back to compression.
Wait, why? Okay, sorry. Why is it back to compression after 4?
Because it only flips on one end of the tube.
So, okay, so, hold on. Here we go. Boom, started.
Flips,
Coming
rarefaction,
back. Refraction, coming back.
flips,
2.
and now it's
Now
back
it's
to
just-
compression, so it's gonna resonate with the first wave.
Got it.
Okay, because we're talking about resonance. So we're trying to build up the sound waves on top of each other with the reflections through them, okay? Because it enforces the sound, right? Which was part of our definition.
Ooh.
I think the confusing terminology in this part is the fact that you can have a half-length or a quarter-length tube of any length, really, in real life. The length in the name does not refer to length in actuality, it refers to length with respect to the length of each oscillation.
Of the wave, yep, exactly. So, we're gonna look at how we do this with math. So we can just figure out which frequencies are gonna be vibrated by what, okay?
Got it.
And that might clear up some stuff. Okay, so half-length resonator. It's open at both ends, right? So flute produces even harmonic series, okay? I'll show you why it doesn't produce the odd, why the next one doesn't produce the odd ones in a second. All right, it changes phase at each end because it's going from small to large, so it flips phase, right? Okay, that's what you need to know, okay? High volume to low volume and compression and rarefaction switch, right? We're all good on that?
Yes.
Sweet. Good, so now we can use the wavelength equation to figure out where these resonators are gonna vibrate at. Okay, what frequencies are gonna most strongly reinforce the sounds that we're making with the vibrator that's at the closed end, or whatever, right?
Right.
Make sense? Good, so R is the resonance frequency, and C is still the speed of sound, and 2 of the length of the resonator. Okay? So let's look at how we do it. So our flute is gonna be 0.5 meters long, so like 1.5 feet, and if we take 350, we get 350 hertz. That's what's gonna be the resonant frequency of the flute,
Okay.
okay? So if you put something that was 350 hertz through the flute, it would sound louder. It would have more reinforcement of the sound to it, okay? Make sense?
Mhm.
Why do we want to know that?
Because our voices do it too. I'll show you, okay? Good, so think about it, if we do it with the quarter length resonator, there are certain frequencies in our voices that are gonna be louder.
Isn't there just one frequency?
No.
But we can change the length. And
Oh yeah, yeah,
Okay,
yeah, yeah,
so-
yeah, yeah, I love it. Great.
basically the point is gonna be this. We have all these different lengths of tubes in our voice. So there's really like 6 of them. And we can change all of them. So we can change what the resonant frequencies are.
Amazing.
Okay. Let's go back and learn everything we need to know before we talk about it. Good. So now there's this thing called destructive interference you can have. It's when waves go on top of each other, like so when they reflect, and they hit each other and they cancel each other out, right?
Oh,
Right. So if you were like sitting in the bathtub as a little kid and you're like, oh, what happens if I like push 2 waves together? It gets bigger. And if I like pull them apart, they cancel each other out, right? Okay. Exactly. So if we have one in phase, constructive interference makes it double the amplitude, right? Yep.
Yes.
Basically. If you have them out of phase, so we have rarefaction and compression at the same time here, you get destructive interference and there's no sound that happens. Okay? Now so, we can actually do this.
I brought my crappy didgeridoo thing.
Okay.
Yay!
So if it, in our voices, if I go like, see how it cracks? It's because there's destructive interference of the sound wave going back and forth, and I can't make any noise at that pitch.
Oh.
Whoa,
Well,
I'm just going, or whatever.
why,
See how it cracks?
Try to sing right when yeah, it cracks again.
when cracks.
You can't sing.
Cracks.
So listen, I'm just gonna go, okay?
Whoa!
So it forces your voice to crack?
This is
Wow.
amazing.
Because it's destructive interference.
Oh,
Right.
your voice is actually like.
It's stopping
It is your
the
voice
sound
stopping.
from happening. Because the pressure, the destructive interference is hitting the wave, and so I can't sing that pitch. Through this tube.
Even though you are singing the pitch.
Even though I'm like trying to, it's stopping my voice from doing
That
it.
principle has
Oh,
to
it's stopping your
influences
actual
where our
flute?
passaggio is, right?
No.
Sometimes, yeah. I mean, so like we have so many different lengths of tube in our voice and everything. The destructive interference like plays a role in our singing. So if I sing something like ooh, and you can't hear it,
Yeah.
there's like some destructive interference in that.
Right.
But it's not like we can't stop ourselves from singing with our throats. Like we can with this.
Okay.
Okay.
Yes.
Does that make sense? Anybody want me to do it again?
Yes.
So just listen.
Tommy wants to try it.
What?
Tommy wants to try it.
No, I
Okay, you
don't.
can try it after class.
Okay.
I have one that's like super long at home, and it's like really obvious of that one. It's because the pressure is greater. Okay, good.
Cool. Great demonstration.
Okay, half-length resonator. What did we not talk about with this one? Ooh. Because it's open at both ends, it gets half-length. I think we talked about all this eventually. Okay, so you need to know this equation. Okay, the R equals C over 2L.
What's the last one? How is that different from the last one?
It's the same as the one we just talked about,
Oh.
because this is still half-length. Okay, so if it's quarter length, this one, it's going to change the equation, right?
Yes.
Because we only have a quarter of the wave.
Cortex.
Yeah? Whereas with this one, we have half of the wave. Makes it before it has to. It's abstract, right? Okay. Alright. Clarinet and voice are quarter wave resonators, produces only odd harmonics. Okay? Because it skips the even, or it skips the even ones. Everybody got that? Because of the way that it resonates. Okay, good. Changes phase. Math is really complicated. Good, so the equation for this one is 4L for the length, because it's not half length, so it's not 2L, right? Good.
Oh, for the voice.
Yep.
That's already.
Voice is closed at one side, right?
Got it. And for clarinet.
So it has to go through the wave 4 times until it's back to where it resonates, because it'll resonate when it stacks on top of each other, right? What we're trying to do is get constructive interference, right?
Yes.
To make our voices louder.
Right.
Or more resonant, is that. And so when we go 4 times through that, we get the constructive interference, because that's when it matches. Okay? Make sense? Is anybody confused?
Can you go back to the other slide?
Good. We're in this one. We good?
Good.
Good. So our standard vocal tract is 0.7 meters, so it's 17 centimeters. That's like a guide. Okay, so it's like my voice or something like that. They could be really short, so like females, it could be like 13 centimeters or something like that. You know, so it changes where the resonant frequencies are, and this is where you change where your voice like has a break or something like that. Okay, this affects that. That's why the length of your voice affects what voice type you are. Okay, so if my voice is longer than Jack's, that's why I'm a bass and he's a tenor. Because our resonant frequencies are different. Okay? Yes, Chelsea.
Can you explain the difference between the odd and even harmonics?
Yeah. So this one, it only creates odd harmonics because it cancels out the even ones. Because of that.
I understand why it's happening, but I don't understand which harmonics are odd and which harmonics are even.
So the first ones are the even ones. So, right? First, second is even.
Yes.
Yeah.
Of that scale?
Third harmonic's odd.
Okay.
Yeah.
Of the scale?
Yeah.
Okay.
Exactly. Because harmonics only happen in the way that we talked about. They only happen at an octave above it because it's in frequency, right? So it happens at hertz times 2. So if it's 110, it happens at 220, then it happens at 330, then it happens at 440.
Okay.
Make sense?
Yes.
It's okay if it doesn't. Okay, cool. We got enough time to talk about this. So that's okay. Good. So if we're at 17.7 meters and you get this resonant frequency, we do our equation, right? So 350 meters per second, 4 times 0.7, we get approximately 514 hertz, which is what note? Does anybody know? There's a chart in the back of the book, if anybody has it.
B,
B, I think it's something like that.
B flat, or B, maybe C. Both,
Oh.
definitely not D, that's too high.
P.
Probably B,
I think
I'm guessing B.
Yeah, it's like B and C. Okay. So, and remember, it depends on temperature. Something's right. Okay. So that's where, like, the break, the first passaggio we get in male voice is like B, flat, C, whatever, depending upon how long your vocal tract is. Okay?
Mhm.
Makes sense?
Oh yeah.
Makes sense. Okay, and it happens with women too, right? Because you have the same, you're doing the exact same thing that we are. It doesn't have anything to do with chest and head voice. This part doesn't. Okay? You know how like you all have like that, like when you go into chest voice and it's like around middle C or something, or it's like the bottom of the staff? It's the same reason. Okay? Cool. Good, so if I have a didgeridoo, which is this thing, mine is 1.5 meters long. Okay? So if we do the equation, and it's closed at one end, right, when I play it, what will the resonance frequency be? Can somebody do the math?
Oh,
You can use a calculator.
Yeah.
I don't.
Is anybody doing it?
I'm
No,
doing
I'm
it.
on.
Awesome.
Tommy's gonna beat me now.
Uh-huh.
76.0.
Yep,
Oh.
cool, which is what no?
Jeez.
Which is what?
What no?
I don't know.
Well, look in your book.
I don't have my book. You said I didn't have to bring the class.
Okay.
Let's see, this book says it is
76, is that what we got?
74.63.
C2.
This one says it's D sharp. Why don't you memorize your frequencies? Okay, cool. So if I play it, it should be D sharp, right? Right?
That's it.
Which is
Math.
math,
That's
right?
Jesus right there.
Does everybody see how that works? Cool. So that happens at higher frequencies too. We don't have to have our tube be this long. That's why that note is so low. But ours, our voices are like this long. Actually, I have this thingy. I'm glad I brought it.
Me too.
So this is like models of voice track. Have you guys ever seen people use these?
No.
No.
Okay, so it's like a duck call. On the end of this is like 17 meters. Okay, so if I play it like,
I like it.
Okay.
We all sound like
is that right? Well, I mean, so like, there's a lot more. It's like, and then you stick it through the resonator and see it accents a frequency, right? And that's how babies act. Okay, that makes sense?
Yes.
Yes.
Okay, that's how resonance works. So we get, in our voices, there's like 6 or 7 different lengths of tube that happen like this. So remember that the compression rarefaction change happens when it changes from being a smaller space into a larger space, right?
Yeah.
It also goes the other way, right? So from the larger space and go into a smaller space, the sound will change. Like have you ever gone into like a tunnel or something, and there's like a lot of like sound, like city sound outside, and all the sound, it sounds really different? That's part of the reason.
Wow.
Okay, good. So we get differences, right? So this, and it has to do with the size of the opening and not really the shape. Okay, so you don't really get a change when you go oh, like if it's oh or oh, you know what I mean? It doesn't have to do with like how round your lips are, it just has to do with how much area is getting switched. Do you know what I mean? So it's oh or oh, it sounds different, right? Because it changes what frequencies get reflected. So we get about 7 of these. They count this one between your teeth and your lips, and I don't know.
It's like people sing like, you know, and it does stuff.
Every shape you make does stuff, right? Because it changes all of this stuff. So down here, this is like where your vocal folds are, right? And this is your epiglottis, okay? So we get like that length. And then we get this one, this is your tongue, right?
Look how high that
yeah.
is.
So that's really, so what vowel do we think that is?
E or something.
Yeah, but the tongue's like really far back for some reason.
How come it's like 6 to 7? Like, is there not, it's not a C?
Because they count this one, between your teeth and your lips.
Oh.
And that's like, most books will say 6. But this was
Oh,
like,
I see.
this was like an ENT paper that I got this from, and they're like, oh, 7, we have to be exactly right. Okay.
Well, I would always want to be exactly right.
Well, but the thing is, you can't really change this that much.
Okay.
I mean, you can, but it's not gonna, you generally don't wanna move all that much.
According to your vocal technique.
According to my vocal
Well, it's not a ooh, it's not a ooh.
This is
it's
not pedagogy.
just- well,
Yeah,
but
good.
I think it can make a big difference. I understand why they say 7.
Yeah, okay, you can say 7. It's 6 or 7. The
Great.
McCoy book says 6, I think,
Good.
right? Does anybody remember?
That's what
I think he said 6. But it has to do with that. And then like you can change these, so like if you made that this was the same, that this one didn't happen here, then you'd only have 6, right? So we can like add them or change them depending on how we shape our mouse.
See.
Okay?
Yeah.
It's really weird. Good. Alright. Things to remember. Oh, it takes 0.0005 seconds for this to happen. Because we're doing it at the speed of sound. So it's right? Okay. It's possible to achieve destructive interference sometimes at our lengths, but it doesn't, we don't hear it affect our voices like we did with my example of it, okay? There's 6 resonant chambers or 7, you can write whichever one you want. But just know that there's like that many of them that we can change. So we almost get up to like 3 million different combinations of resonance that we can make with our vocal tracks. And that's why it takes us millions of years to learn how to sing, right? Cool, all right. So does everybody understand everything?
Yes.
For sure, okay. So we'll have questions next time, but I just want to watch this video at the end, okay?
In Voice Flame Extinguisher, Adam and Jamie investigated the viability of fighting fires with sound waves. But what we didn't have time to show you was when they explored another fire phenomenon, the Rubens tube.
This is a stunning visual representation of a sound wave.
Yeah, let's fire it up and see what it does.
All right.
It's a classic physics experiment that has recently become an internet phenomenon. A length of pipe is perforated along the top and sealed at both ends. One seal is attached to a small speaker, the other to a supply of a flammable gas. The pipe is filled with the gas, and the gas leaking from the perforations is lit.
Oh, it's beautiful.
So this is called a Rubens tube, right?
Yep, it's Rubens tube all right. And what you're seeing is a standing
Now watch
wave
it
rendered
change
in
when they change the
fire.
pitch.
This is how it works. When the guys play a tone through the speaker, the sound wave enters the tube, and the confined space creates reflections and interference, which combine to create a standing wave. The standing wave affects the air pressure inside the tube, which affects the amount of gas coming out of each perforation, which affects the size of each individual flame.
What we're looking at is areas of higher and lower compression being made by the sound waves down the tube, affecting how much gas comes out of each hole.
If you keep the frequency constant, you can determine the wavelength by simply measuring it with a ruler. And if you think it looks familiar, it probably is. Rubens tubes have been around since 1905, when Heinrich Rubin fired up the first.
Look at that. Yeah, we're watching the waves pile up. Yeah, totally. That worked. That is very, very, very cool. I had not imagined that there was such a clear visual representation of the sound wave.
All the way
It's
closed?
okay, so a standing wave is what happens when it's a closed, like closed room.
Interesting.
So it stays the same the whole time. But so if they have like the pitch in it, but remember that like it's escaping through the holes in there, so it's not exactly perfect. That's why it was like had some weird flames and everything, right? Okay. But the biggest thing you notice when they make the frequency higher, the flames get shorter and closer together, right? But they're not as high because there's more compression spread across the thing, right? Does that make sense?
Mm-hmm.
Do you all need to know more about what standing wave is?
I don't know, do we?
I don't know. Ooh. Okay. Well, standing wave's just like when you have it like enclosed. So there's actually like standing wave frequencies in this room, and right now, yeah, because you can measure like from the ceiling to the floor, and that's why there's the acoustic panels, because they mess up the standing waves. So there's not as much reverberation at certain frequencies. Make sense?
Yeah.
Anybody have more questions? Should I let you leave early? Alright, good. So make sure you do the homework for next time. Read chapter 4 on formants, which y'all have been asking me about since we started this class. So. Alright, thank you. Oh, and next week, just so you know, the homework we have next week requires you to use this computer program that only works on a Windows computer. So you have to like use it for it, something like that, okay?
Please send me that one too.
It's tomorrow.
This is your magnificent.
Put it in my mailbox. It's in where all you guys are.
I'm gonna go.
Just put it in my mailbox. Let me know that you and I'll be. Oh, so just send me an email.
That's great stuff. Oh my god.
So,
I've noticed, found out that, I don't know, I was fiddling around with bottles and blowing over the top of the bottle, right? How come if you apply more air pressure, you can get it to resonate at the higher frequency? Or maybe not
because you're splitting the wave.
Okay.
You're splitting the wave. Okay, so you know when clarinets overblown?
Yeah.
It's the
It's the
exact
exact
same.
No.
same thing. Oh, okay, cool. I was
You
curious.
split the wave in half.
I just
And then you change. That's exactly, because it goes up and down, right?
Yeah, okay.
Go regular.
What are you guys doing? Just staying here?
I think my main genius. We have class. We're about to.
Yeah.
Wait, did you just tell me we're about to go get coffee?
We are about to do.
Okay.